Okay.
Right.
Hey everyone, welcome to yet another RL Theory seminar. This week we've got Gergi hosting. Say
Hey,
hi.
everybody. What's up? Hey, I'm Gergely. It's good to see everybody.
And Ching-An will be presenting. Ching-An is
Hey.
a senior researcher at Microsoft Research, and he's here to talk about Armor, a model-based framework for improving arbitrary baseline policies with offline data, which is actually quite a mouthful. Ching-An, do you want to go ahead and start?
So thank you for the introduction. So today I want to present our paper about armor, and this is also recently accepted to New Rips this year. And before I start, I want to really shout out to my collaborators, Mohawk, Byron, Tenyang, and Nan, who are also like behind this paper. I'm just here to kind of like presenting them. Um, all right. So let me start by with a motivation. So I want to ask a question. So if you think about, let's say, I want to build a robot that can, let's say, fix, let's say, your, let's say, cars or like furniture or cook for you, or building an autonomous driving car, or building some kind of like agent that can automatically diagnose like different diseases, etc. Like, what does it take? How can we actually build this kind of like autonomous learning agent, right? So here we're at an RL like theory seminar. So let's think about like whether RL can help, can solve this problem, right? So RL, at least we think about, if we do exploration, let's try the simplest thing, let's say like UCB. Under certain assumptions, we can explore everything, and then we can show purple guarantees in terms of, let's say, regret, for example, right? But if you bring this amazing algorithm that we proved to a practitioner in these fields, they might have some questions about like whether I should run this algorithm or not. I think, and this is probably not an issue about, let's say, computation between, let's say, like, there's a guy in theory that we prove things and then we don't know how to implement it. Let's say we can perfectly implement them, like not a computation issue. There's still some like hesitation in really using this algorithm, amazing algorithm that we developed, and they are perfectly correct. And one reason is that like exploration in the real problem, in the real world problem, is not free. You cannot just let the agent to try different things and then hopefully that and run algorithm like that. And the main reason is because that like in a real problem, like every real decision that you make have real consequences, right? A wrong action can potentially break the hardware or cause someone to get hurt. And so learning in the real world problem is not just about let's trying to have a like let's say a small sample complexity. It's also a matter about like how much cost that you will incur when you actually run this algorithm. Some action are just like easier to take and then versus the other ones. And so this is really because data collection in this real world problem can be very costly and risky sometimes. And if you think about that, like even resetting, let's say a robot is not free. Right? You see that here when the robot falls down, you have to manually reset it to the original location. Whereas in the theory, you say, yeah, that will be the next episode. So this kind of thing is quite different. And also that like I talk about like permanent damage that it might be caused by exploration, but there can be also be ethical consideration, right? So imagine that I want to run RL to kind of like recommend, let's say, different drugs for patients, right? For the patients, it's trying to get the best service it can from an AI system. But for our own sake, we might be doing exploration, and as a result, that we might have an ethical consideration not reviewing this exploration process, and as a result, that it might potentially hurt the patient, right? And on the other hand, if you think about this more on the commercial front, if you already have a running system, such as let's say a service on let's say Windows or iPhone, right? If you want to do exploration to make it better, it might potentially, let's say, make the user experience worse. As a result, that you might lose a customer forever without ever coming back. And so these are kind of costs that like real exploration might actually incur and suffer. As a result, we need to think a little bit more carefully when we think about, let's say, how to learn, do learning in these real world applications. By the way, feel free to like stop me anytime if you have any questions. Okay. So in practice, what happens is that the data we can collect are usually can be done by qualified policies. By qualified, I mean that policies satisfying certain, let's say, safety or performance criteria, such that like people are willing to, let's say, tolerate running them in the real system. But the good news about this is that like we actually already have tons of data out there. And because usually we are trying to apply learning to something that already exists and want to use learning to improve its performance. But this data has some like qualities. And one important quality is that like, even though we have large data, they don't cover all the scenarios because they are not really exploratory data. Because if they are exploratory data, it means that this application probably doesn't have this exploration issue. We can probably just run out at the beginning. And so the question here is that how can we learn from this kind of like offline data that's not exploratory, doesn't have full coverage, right? So for example, if you want to, let's say, design an algorithm to for autonomous driving, here we have large data like telemetry data from like driving cars, but most of the data are safe data. Few of them are unsafe. We are not going to, let's say, intentionally recreate unsafe data, and so there's a large bias in the way the data behaves. And this is kind of the reality that we need to deal with. So, so this brings the idea about, yes, reinforcement learning. If you do exploration, you have this issue that I mentioned, but there's offline reinforcement learning. Can they solve the problem? And to, let's say, I would say 80% yes, but there's a 20% which is not really like considered before, and that's what this paper is going to be about. So let me just give you a highlight about how offline reinforcement learning work in general. So offline RL is kind of like a modern version of batch RL where like it relaxes the assumption that the data needs to have full coverage. And it's using the principle of pessimism. And the core idea is just trying to optimize the performance lower bound since we don't really know what the true performance is. Right, so this is kind of similar to like majorization, minimization in optimization literature, where you have an objective, you want to maximize it, we don't know its exact value, and now we construct a global lower bound of it. And this lower bound is guaranteed to be tied at certain places, and in this case will be the places where we have data. And by maximizing this lower bound, we are guaranteed some things, right? So we're guaranteed that we're going to be better than where the value that we see in the data because we know they are tight. And then we can show some kind of regret guarantee as well. So this can be summarized by these two sentences. So we know the lower bound is tied at the data, so it's going to be better than the data collection policy, right? So this is kind of following by this majorization minimization idea. And on the other hand, we also can have a guarantee to pi star, which is the optimal policy. And roughly you can think about, yeah, this gap, this regret will depend on how much pi stars, let's say, state action visitation is covered by the data, right? Because I know that if my data cover those places, the lower bound will be tight, as a result, be better. And naturally, you can think about like, yeah, naturally, the gap will be relevant to the data coverage and its relationship to pi stars distribution. So this is the rough idea about how offline RL work. And the reason why I say there's a 20% left in this field, at least theoretically, is that there's a catch. Like usually, yes, in theory, we can prove a lower bound, and by assuming somehow, let's say, the bound on the reward, etc., and then so we can put it like some constant and then show, yeah, this is the lower bound due to some concentration. But this hyperparameter is usually not very tight, and we usually don't really know like what the best hyperparameter to use is. And especially in this case, different hyperparameters will usually lead to very different results, unlike in online RL. In online RL, if I set, let's say, the coefficient in front of the, let's say, the boundness to be wrong, eventually will still converge just slower. But here we don't have that kind ability to collect new data. So we construct lower bound, we optimize it, and that's it. But now if you choose a different hyperparameter, it will lead to very different results, and that's kind of the real issue. So here's an example of a lower bound constructed maybe by a well-tuned hyperparameter I manually selected by drawing these figures. Here's another one, which is more pessimistic. We're trying to be more aggressive in penalizing the value that we haven't seen in the data. Here's another one that's less pessimistic. It might fail to be a lower bound sometimes if you, let's say, set up a penalty to be wrong, right? So these different hyperparameters will affect the policy pi hat that you get, and they can be very, very different. And that's causing an important issue, which is that, like, since in offline RL, we don't really know which one to pick. The one we get from theory can be very loose. As a result, what will happen is that the policy that you learn might actually be worse than the policy that you begin with, which is the policy that you're running in the current system. Here I'm denoting that as pi ref, right? And the main reason for that is that if I pick the wrong hyperparameter, or when this pi ref is not the policy that collect the majority of the data, the resulting lower bound will be going to be loose for that pi ref. As a result, even I want to try to maximize this lower bound, like the resulting policy might actually have a worse performance than my current policy. All right, and this performance degradation has like issue of like cost and safety and ethical consideration, right? Let's go back to the driving cars example. I have something that's already running. Now I collect lots of data. Now I want to upgrade my system, right? So if I don't do this very carefully, my system might break, right? In the sense that it might not the new, let's say, updated firmware might cause a car to crash, right? Similarly, you can think about like very, let's say, tremendous bad events that can happen in a medical scenario as well. So basically, in scenarios where like the consequence can be very important, this kind of performance degradation can be like a very serious issue. So in Armor, our main motivation is trying to.
Can I have a question here? Yeah. So yeah, I buy the premise that you're explaining here, but there's one question that I have here, which is like, is this a realistic concern that the reference policy would have a lower bound that is very loose? Because typically the reference policy is what was used to generate the data, or at least that was the scenario that you were explaining. And yes, typically for that, you would have like a very good estimate.
Yeah. So the lower bound, so it can be loose for mostly two reasons. One is so once is that the reference policy doesn't generate any of the data, and it might even be outside of data support and can be loose, right? But on the other hand, it can be loose because it's not the only policy that generates the data. There can be multiple policies. Let's say imagine I have these systems, you have different generations, right? I have all kinds of log data. The policy, the data generated by the current policy only takes a small portion of it.
Right.
And as a result, like the statistical looseness in there will kind of make it loose at that point as well.
Right. Okay. Gotcha.
Yeah.
Thank you.
Yeah. So this is really the main motivation of our work, Armor. So we are trying to think about a way to do offline learning that can essentially generate a lower bound that's going to be tight at this reference policy. As a result, we can address the issue of performance degradation. And so our key idea is to really directly optimize the performance difference between 0pi and 0pi reference. And you might think about that, why, let's say, optimizing an absolute performance versus a relative performance might lead to different results. And this is due to the missing data coverage, because we have some uncertainty about how different things works. As a result, like optimizing for an absolute versus relative concept, it will give you different policies. And this is different from online RL. Let me give you a toy example to explain this. So suppose that you want to take a bus or basically go to school, right? You can either take a bus, walk there, or bike there, and they might take different times depending on the traffic, right? But you don't, at the bus station right now, you don't really know what the traffic is like. And so here you can think about that, like, yeah, there are case 1 and case 2 with good traffic and bad traffic. If you think about the best solution in the absolute sense, the one that takes the least amount of time, then the worst case, in the worst case, but in the that takes the least amount of time in the worst case, then you either walk or you'll do any of those, right? So because in the worst case, they are going to be the same, will be 30 minutes. But if you think about the relative things, about what is the option that's better than taking the bus in the worst case, then in that sense, now it's going to be better. As a result, you'll take the bus. So if you think about things in the worst case, think about the unknowns, like think about in the absolute term and the relative terms will give you different things. And that's the main point I want to point out. And so in here, we want to kind of extend this concept in general to offline RL by thinking about, yeah, I want to maximize in the performance difference. But now I'm thinking about the worst case in the performance difference. So here I construct a lower bound by taking the minimum of all possible NDPs that can potentially happen in this world, and among the set that is consistent with the data that I have seen so far. So this origin block here essentially will be a worst case performance estimate, or like a lower bound of the relative performance between 0pi and 0pi reference. And assuming that this class of, let's say, model M alpha contains a true NDP, which I don't know. And I'm going to show you how I construct this confidence interval to contain the true model M star. And if I do so, then under very mild assumptions, I can guarantee that this performance lower bound will be very, very tight at pi ref, will be exactly 0, has a 0 gap at there. And that means that I will have no performance degradation, regardless how my data cover and how, let's say pi ref is used to collect data or not. All right. So now let's jump to the more mathematical part. So here I just want to like bring out like the standard problem selector so that like we are on the same page. So here we consider an MDP setting, and the true model is denoted by some P star and R star, which I don't know. And here we have some like offline data set of transition tuples collected by some behavior policy. And here the behavior policy can be some like mixture of policies, etc. And it can be different from pi reference. And our goal is trying to maximize the discounted return. So here we consider discounted setting. Okay, and here we make some like modeling assumption. So we assume that like there's a model class and a policy class. A model class, we are going to take a model-based approach. So the model class is something that of MDP models, and we assume that this model class contains the true MDP that we want to learn. And there's a policy class, which is a policy that we want to search over. And we assume that the pi ref is in the policy class. This is a very mild assumption because if pi ref is not in the policy class, since I'm going to assume that I have pi ref at my disposal. And so I can just always add pi ref in my existing policy class. So this pi ref in the policy class is a very mild assumption. It's almost nothing. All right. So we want to optimize this lower bound. And the way we construct it is to construct a hypothesis class, which are the models that are consistent with the data that I've observed in this data set D. And so these are essentially the models whose, let's say, empirical training error are very, very small within an alpha compared with the optimal empirical minimizer that I have. And here I define the empirical training error as essentially the negative of the log likelihood and the square error on the reward. Here I have a scaling factor Vmax, which is the largest value of the value in this problem, and as a normalizer, so that like this log likelihood and the reward scaling are kind of in the same range. And so in the following, I'm going to choose alpha essentially to kind of like contain M star within this hypothesis class. Here you can already imagine that like if I set alpha to be infinite, then this will be true trivially because it doesn't basically impose any constraints. So you can imagine that the larger the alpha is, like you're going to contain it, but the question is that what is the smallest alpha that you can get? So the first result that we have is that like if we make that previous realizability assumption, which are, let's say, M star is in my model class and pi ref is in my policy class, then for any alpha that's large enough, I don't really care what the value is, so long as it's not that too small with cutting that threshold that we're going to talk about. Then this policy, this lower bound will be tied at pi ref as a result that the learn policy will be better than pi ref, right? So this statement has two like parts. One is that it's a policy improvement statement saying that my learn policy is better than pi ref, but it's also saying that this is something that you can get very easily. There's a robustness in there. As long as alpha is not too small, this is fine, right? Because the only reason why I need alpha 4 in getting this statement, as I will show later on, is that I need M star to be contained in M alpha, right? And once I have this statement, it means that like my policy is not going to degrade. I will have no performance degradation when I run Armor. And this statement is true regardless how pi ref is staying in the data support or not, or whether the data has full support or not. It's a generic statement. And so we can compare this kind of like policy improvement statement with the kind of like policy improvement that we see in the literature. So here we have the strongest statement that we know so far, which is like pi ref, so RPI, with respect to any pi ref. And in the earlier work, there are like somehow robust policy improvement statement with respect to the data collection policy. And here, they can show that, if there's some hyperparameter, if you set it to be some one-sided value, like very large or very, very small, depending on the sign, then it's guaranteed to be always better than the behavior policy. All right. And let's say there's a more generic statement, which is like safe policy improvement, which is weaker, but it's kind of almost true in all the offline algorithms. And what it says is that if I select the hyperparameter to be right exactly, then the learn policy will be better than the behavior policy. So there's a level on what is the policy that wants to be better off. In the RPI to mu and the safe policy improvement, they are going to be better than the behavior policy. They're not guaranteed to be any like PyRef or the current policy that you have in your system. And there's a degree about robustness. When you move to the RPI regime from the safe policy improvement, it relaxes the dependency on having the right hyperparameter. And since in the offline setting, we cannot really choose the right one, this robustness will be very important in more realistic application.
So wait a second. I don't think that I got the difference between RPI to mu and safe policy improvement. Can you explain this again? So safe policy improvement means a guaranteed improvement over the behavior policy?
Yes.
Did I get that right?
So both of them are guaranteed improvement over the behavior policy.
Mm-hmm.
And so that part is the same. The difference is like how sensitive this kind of like, let's say, impulse improvement property is to the selection of hyperparameter choices. So RPI means that like it can have this property of policy improvement for a large range of hyperparameters. And so, for example, there can be some alpha, such as saying that if the alpha is large enough, then it will be always no worse than behavior policy. Whereas safe policy improvement is just only about policy improvement. It doesn't care about like how you set its hyperparameters. And in many offline algorithms, you only get this property when you set the hyperparameter to be the exact right value. If you set it to be too large or too small, it will break, and it will no longer have this property.
I see.
Yeah.
Right. Okay. Thank you.
Yeah. And so here I'm going to give you a very like quick proof sketch. It's very simple. And so this is really just implied by the fact that I choose a large enough alpha such that M star is in M alpha. And so because I can bound the performance difference by the worst case performance difference given by M alpha because of this M stars in M alpha statement. And since my policy is an argmax, I get a lower bound of 0 trivially. So this is really like the direct property of optimizing for performance difference. And so here I want to just give a quick remark. And so you might wonder, yeah, so if I can improve this policy by using this performance difference objective, can I repeat this and improve forever, right? So here, if I start with PyRef, I get the next policy, and I use that as a new PyRef and iterate this process. Maybe I will get an infinite machine and then just get the best policy in the world and get PyStar. And so in the paper, we can prove that this will actually not work because this operator has some fixed point. And if I learn a policy in this way, this pi hat will be a fixed point and it will no longer improve. And we also show there are many other kind of fixed points that you can prove, such as, let's say, the worst case, let's say, the one that can maximize the worst case absolute performance, and then there are many other things. And so you're welcome to check out the paper for that. And so what I talked about earlier is just that, yeah, there's no performance degradation, but I haven't really talked about what is the true performance of the learn policy, right? So what if the PyRef is not so bad? Can I actually improve that, right? Because previously, meaning no degradation, a trivial solution would be I just output PyRef since I know PyRef, right? So that will be true trivially, but we also want to do some learning in offline RL. So here's another guarantee about its absolute performance, and it's stating in the sense of a regret to any comparative pi. And so here the upper bound reads as follows. It has a term some kind of constant c, and that will depend on how the data cover this comparative policy pi and this PyRef. And I'm going to explain that later. And there's another constant related to Vmax and 1 minus gamma, and that's essentially the scaling of the problem. And finally, there's a square root 10 of a log n. Here I'm assuming that the size of n is finite, but that can be extended using a covering number. And here's a d, which is the size of data set. So that the last term is essentially due to the union bound and the statistical convergence, right? And I want to mention that this is an additional guarantee on top of the RPI that I just showed you. So here we are measuring the coverage by what we call a generalized single policy concentratability coefficient. And what it says is that in terms of an error defined by the total variation distance plus a square error, if this error is small on the data that of the behavior policy, how small that is will be on the distribution generated by a policy pi. So it's about like transferring, let's say, if I see small training error, essentially, how large error that will be on the test distribution, right? So if this is small or bounded, it means that like, yeah, the learning thing, if I just learn things on mu, then eventually the error will be small on the test set. And so that's kind of what it means. And so one important thing I want to point out here in this like theorem, and which is different from the existing theorem in offline IR literature, is that here it depends on the coverage of both the comparator and the reference policy pi ref. And so whereas in the existing literature, you don't have the term about pi ref. People might have different, let's say a notion or way to measure coverage, but you end up with something constant that's depending on pi. Here, the additional thing here is a pi ref. So what it means is that if I care about convergence to the optimal policies performance in terms of regret, I need both pi, which is now the optimal policy to be within my coverage. In addition, I need my pi ref comparator to be also within my coverage. So so you can also think about that, like, yeah, if I set my pi ref to be the data distribution, then I will get the optimal policies guarantee, right? If my the optimal policy is within the data coverage, and this will Armor in this sense will behave very similar to existing offline algorithms and have their guarantees. But here it means that like there's no free lunch between having no, let's say, performance degradation and a very good absolute performance. If my pi ref is very bad, right, and somehow it's also out of data distribution, it means that, yes, I will get a policy by the previous RPI theorem that's not going to be worse than pi ref. That's for sure. But at this case, this like absolute performance guarantee bound will be vacuous. In the sense that, in that sense, this C of pi ref can be infinite, and this bound doesn't mean anything, right? So there's a thing we need to kind of like trade off between like being robust to be performance degradation versus like getting always the right absolute performance. And in this bound, you see here I set alpha to a very specific value. So this is something that's similar to the existing offline RL. You need to set like the hyperparameter to be right, just right, to get a performance guarantee. And this is kind of similar to like how people kind of prove that a safe policy improvement before. You need to have a right hyperparameter to do that. And so this is kind of the trade-off I want to mention. Okay. So if you have no questions about like what those theorem means, then I'm going to just tell you like how this theorem can be proved. And it's actually simpler maybe than you thought, even though like the result is quite nice. So here we first going to define the lower bound of the performance difference of J of pi and J of pi ref, and by this like n minimizing over this like m alpha set. And here I'm just going to like assume that alpha, if I say to the value I showed above, that this m alpha will contain the m star, and you can find the detail in the paper. So once we have that, we can just expand the difference by introducing this lower bound and decide the performance of pi ref, right? And now since we know pi hat is the optimal solution that optimizes lower bound, we have this upper bound, and then we also know that like this lower bound is a valid lower bound for any policy pi, so it's also a lower bound for pi hat's relative performance. So that term will vanish, and what will be left here will be something that's like very standard, which is like how much your lower bound underestimate the target value of the comparator, right? So here we are talking about the performance difference. So it's about how much your lower bound will underestimate the performance difference of your comparator pi to pi ref. So this is kind of a standard term that you will see in, I would say, 99% of the offline R analysis, right? In the exploration one, you see a different direction, but yeah, how it works. So what's left right now is to really quantify like how large this underestimation is. And here's a lemma. It's essentially depending on the coverage constant and somehow like statistical concentration rate. And now I'm going to prove this lemma. So to prove it, like the first step we can do is that we can expand this performance difference. So it's a difference between, let's say, J of pi and J M of pi, which is kind of like the performance in the true NDP versus the model NDP for a policy pi. And you can expand it by performance difference lemma or like the simulation lemma, either way. Then you can upper bound like the difference in distribution by a total variation distance, and that's what you will get, right? So you see it depends on like the difference in the reward function and how your model transition and the true transition differ in every time step in the sense of total variation distance. And then you can apply Cauchy-Schwarz. And by substituting the definition of error I'm showing here, which is what I used to define the concentratability coefficient before border coverage. And so once you have that, you also like upper bound it by the definition of this IC. And we're almost getting there. And the remaining thing is like we're going to upper bound the error on the data distribution by essentially like the concentration. And since we are selecting our model to be like small in terms of like the empirical error, right? And once you have everything here, you get this lemma and you get the final theorem. So in summary, I want about what we have talked about so far. Like I showed that like Armor can learn policy by solving this kind of two-player game, and the benefit of that is that like it's going to be very robust to like the hyperparameter choice and the quality of pi ref and the data distribution. Regardless of those, you always get like the guarantee of having no performance degradation. And if the performance degradation is what you care about very much, and that's going to be important in, let's say, safety critical or decision critical applications, then this is a very good algorithm. On the other hand, we also show that like it's not just outputting pi ref, it's doing some learning. So we can get some performance guarantee in the absolute sense as well. And we show that like here you get a performance guarantee like this, similar to what you see in the offline hour literature. And with the exception that here you have additional constant C, depending on the coverage of data to the pi ref distribution, right? And this is a no free lunch, as I mentioned before. If you want to have very good performance, you need both of them to be within the coverage. And this is something you have to pay in order to have a robust policy improvement or no performance degradation guarantee. I saw a question.
Yes, thank you for the presentation. My question is, can you replace this performance guarantee that you have with the coverage of pi hat instead of pi? So imagine I don't know the optimal policy, and so I would like to have a like kind of empirical Bernstein bound or something that is dependent on.
Yeah, I think that's a good question. I think that is possible. I need to think. Maybe we can discuss in the later half of the talk, 30 minutes. And I think I've run into something like that before. But the main reason why we want to write things in terms of, let's say, not depending on pi hat is because that like we don't really know like where pi hat will go. And so we want to write a bound origin, let's say, in this kind of like worst case sense about like depending on something that's fixed there. Yeah, but I think it's kind of possible. Basically, I think the trick probably is going to be in here. Before we kind of like switch everything to the worst case to be just about like to be in the basically. So here you see one line where we just drop entirely like the which is this line, the no greater than 0, right? We use a lower bound that like lower bound is lower bounding the pi hat part, and if we probably use it at the other way to use it for the when you introduce let's say not lower bound at pi but at pi hat, you probably get a different results. But I need to think about that. And so I think that's probably possible, but usually the reason why people want this kind of results instead is because that if I don't really know beforehand whether my pi hat will be out of support or not. As a result, I cannot control C.
I see. Thanks.
All right. Right. So I have 20 minutes. Okay. So here's just another way to kind of quickly visualize what we have talked about. Right. So you can think about offline RL in the sense about whether they are optimizing for an absolute objective or a relative one. And for the relative one, you think about whether they are relative to like a behavior policy or an arbitrary policy. And I want to mention that if in Armor, we are assuming that pi ref is given. It's not something that we don't know. If we don't know that, we cannot do any of those, right? So, and for different kind of versions, you get like different kind of guarantees. Like RPI to any pi ref is kind of like the strongest one that we know, but it needs knowledge of pi ref. The second to that will be like to the behavior policy, and the rest will be set policy improvement. Yeah. And so I know that we are in an RL theory kind of like seminar, but I want to show that this algorithm is actually implementable, and it's kind of very competitive with other like deep offline RL algorithms. And here I'm going to give you some like highlight about how we actually implement this idea and make it efficient and scalable. So yeah, so originally we start with a two-player game, right? Think like, I have to do a max and do a min, and then solving each step is actually very computation intensive. And so here the trick that we use is that we are going to implement this like by a model-based actor critic. So I'm going to expand this difference in the model performance in the difference of like Q functions and with a Q function that is consistent with the model. And so now I have these following terms. And so I'm going to learn actor critic by having my critic my actor to maximize a critic. And I'm going to train the critic and the model together as an adversary to the learner, which is the actor. And so here the critic, I want to make it to be the model consistent critic. And also I want to be pessimistic, right? So it's going to minimize the Bellman error with respect to the model, not the data, but the model. And it also minimizes the performance difference, which is something we see in this term. And our model will just be minimizing the Bellman error because they have to be working together with the critic rather than in two steps. And it will also minimize the model fitting error because I want the model to kind of like fit the data right. And we're going to kind of optimize this by a 2x scale like SGD algorithm by having actor at a slower rate and the the adversary at a faster rate. So if you are familiar with like online learning, you know this will be kind of like a no regret reduction where like the inner one is playing the best response to the outer player, where the outer one is kind of doing like a no regret slow update. So it's kind of mimicking that structure. But I want to kind of like acknowledge that like we don't have any kind of proof guarantees computationally for training deep neural network with this update rule. But it works out, and it's kind of inspired by how as we can prove, let's say some kind of like let's say this had no best response framework for solving like minimax algorithms problems. And the actual algorithm looks like this. So it has it's an iterative algorithm. So this algorithm keeps a buffer of state and action, and they just keep accumulating. And that this buffer starts from the data that you have. So the important part is that we don't keep a buffer of a reward and the transition because that's going to be predicted by the model. The buffer only keeps state and action. And so we have this buffer, and we call the model to predict the reward and the next state. We use this prediction plus the SA together to kind of construct this perform different step error, the Bellman error, etc., and the model fitting error that I talked about, where which is the one the adversary will minimize. Except the model fitting error, of course, is going to fit the true data, but the difference error and the Bellman error is going to be defined by this prediction because we want this actor critic to be like consistent with the model, not the true data. And once we have that, we're going to take a small gradient step to maximize the critic and update the actor. And then we're going to roll out the policy of the learners of currently I have, as well as the reference policy using my model to expand the coverage of SA that I put in the buffer, and I repeat this process. So now you can imagine that eventually, roughly speaking, the model and the critic that you get will be roughly consistent with each other, except it's going to be a little bit pessimistic because I'm minimizing the performance difference to the current policy. All right, and so we test this implementation. I call it implementation, not algorithm. Algorithm is the theory one. This implementation on the very popular default benchmarks. We test it on the Mujoko task and Arbitrary task, and we want to verify two things: whether the RPI property, which prevents performance degradation, actually holds in practice in at least in one implementation that we have, and whether this implementation can be very competitive with other state-of-the-art like offline RL deep learning algorithms. So first, I want to verify RPI. So here we are taking an expert policy, a near expert policy as a reference policy. And this policy is going to go out of support of the data set that we have for offline RL. And because in here we construct a data set of offline RL by non-expert mixture policies. So they are collected by multiple policies, but none of them is expert. And want to verify that, like, if I set alpha to be large enough, the learn policy I have will be no worse than the reference. So this is like setting very high like bar for like testing RPI results, because this will be like a very high performance that you cannot get by just looking at the data potentially. So here are the results. So here the yellow one is the performance of this near expert policy. So that will be the bar we want to beat, or at least be no worse than. And this like the green one is what you will get if I run Armor in just in the offline RL mode without using the information of PyRef. So in that sense, I meant that I run Armor by setting the reference using Armor as a behavior policy, not this expert PyRef that I'm testing here. So this gives you the baseline performance. Now I show the results of Armor with different alpha, and here like the numbers shown in the legend are 1 over alpha. So the closer it gets to 0, the higher the alpha is. So I want to show essentially like if this number is smaller, it's no worse than the yellow bar essentially. And we see in most cases it's really like that. I mean, there's some exception maybe in the human but there's also a large like error bar as well. But you can see a trend that like if I set alpha to be very large, which is a very small number in this 1 over alpha, it's going to be very similar to this like PyRef performance. And when I increase it, it might have some like small room to improve a little bit, as you see in, let's say, in the pen clone and some kind of like the environment in the second row. But as I increase it, which means that the alpha becomes smaller, it will get worse eventually. And so you see this trend about robustness, and there's usually a very nice trend about like yes, you can basically start from like small alpha, a small 1 over alpha, and gradually increase it empirically, and to see like a sustainable performance guarantee without degradation. And we also test Armor as a standalone offline RL algorithm, meaning that because in general, like offline RL doesn't really need an external source of PyRef, right? So I'm testing this Armor here without PyRef. And what I mean is that I'm really just saying the PyRef used by the algorithm as the behavior policy. I can kind of reconstruct and estimate the data. So it can run in the setup of offline RL algorithm. And here we see that it's kind of the best offline RL algorithm that is model-based. And it's very similar to the best you can get in the model-free version. And the margins are very small. It's probably up to the standard error. And one thing I want to also like call out here is that like among all the model-based methods that has been developed so far in terms of like the deep offline RL, Armor, this implementation, is the only one that doesn't use an ensemble of models. All the other methods, even though they sometimes derive their, let's say, intuition or the algebra derivation without an ensemble in mind, eventually in all the implementation, they learn ensemble, and they are using the ensemble to provide the pessimism they need. But the catch of using ensemble is that it's not a very scalable way if you want to like now train very large model using, let's say, transformers. And because like running an ensemble of those will be just like not very feasible right now. And so whereas in Armor, it's trying to kind of like construct pessimism by being adversarial to the learner by solving this as a two-player game. And as a result, we found that it's able to kind of like achieve better performance than those ensemble-based methods, while not using any ensemble at all. So using a much smaller set of models. And this is kind of like very exciting news for us, because so far we've been thinking about that. Yeah, maybe in practice you need to go through ensemble, and but we found now it's actually possible to move away from there, and that means that potentially we can have a more scalable way to scale this algorithm up. So yeah, I want to now have the final concluding remarks. So just as a recap, so in this talk, I talked about a new algorithm called Armor, and that's designed to prevent performance degradation. And the way it works is trying to optimize directly for the lower bound of performance difference to a given pi-ref policy. And by doing so, it has a strong property called RPI to any pi-ref policy, and it's a stronger notion than existing notion on policy improvement, from RPI to just behavior policy or just safe policy improvement. And the benefit of here is that it's going to be give you improvement over the pi-ref that you have for a wide range of hyperparameters that you know beforehand, right? So I know alpha to be large, it'll be okay, meaning that I can say alpha to be infinite, it will definitely be okay. But in that case, you will just return pi-ref. But now you can kind of do a binary search or something to kind of gradually change it while not suffering, let's say, very severe performance degradation, because things will change continuously. And so that makes Armor very kind of practical and to be, let's say, usable in more, let's say, consequence, let's say, critical applications. And we showed also that this idea doesn't just stay on the paper. It can be approximated empirically with some deep learning algorithms. And it's good to kind of see that algorithms that are very deeply rooted by the theory design can perform also very comparatively with other deep RL algorithms for the offline RL. And to conclude this talk, I want to kind of bring out one final question, which might help us to think about in the next 30 minutes, which is that yes, performance difference. I talked about this performance degradation is kind of important issue, and here we are trying to solve it by using a relative pessimism rather than an absolute one, right? But this is always a better answer to is this a silver bullet for all the offline RL problem? Here my personal answer is that I don't think it is, because I think it's really whether you should choose one or the other one is really a kind of subjective and kind of problem dependent choice. Because in some location, I don't really care about maybe that much about degrading from pi-ref that strictly. And by being relative to that, you see already, let's say, it can hurt you to kind of let's say, be competitive to pi star, because I need the data to also be kind of covering pi-ref, which is an additional assumption, right? But in some cases, yes, I don't want any performance degradation. And so that becomes super critical to me. I mean, the thing that, let's say, the regret to pi star is something that's nice to have, right? So you can think about for those applications, almost it's a constraint optimization problem where I want to first make sure that I satisfy the constraint that there's no degradation in performance, and then I want to minimize the regret to pi star, right? But this really I don't think I have the correct solution to this, but I think this is a very good open question to think about for everyone. And with that, I will just conclude the talk, and then thank you for listening, and then I'm happy to answer any questions.
All right, perfect, very nice. Yeah, thank you. So, does anybody have questions? If you have any questions, then just raise your hand. And right, okay. So, Alan, maybe can you unmute and ask a question? If you can. Oh, okay.
Hello? Okay.
Hey.
To go back to the experimental results for a moment, I just want to make sure I fully understand what's being presented there. in the graph section, so med and med replay, etc.
I mean,
yeah, here. So you mentioned there were a few examples where there was you were not expecting performance loss, and I think you mentioned.
yeah. So there are few. So each of them are different data sets, and they are run independently. And so these are mid, medium replay, human, blah blah blah. They are essentially the quality of the offline RL data set. And so they are all kind of like mediocre policies. And so there are few data sets where we see a performance degradation empirically. And one is the human pen, which is in the second row in here. The other one is in the human hammer there. And there is like the door environment, there's also some degradation initially.
And when you say degradation, you're speaking about the first high value alpha, where it's lower than the median between the behavior policy and pi reference.
Yeah. So I'm talking about, I'm comparing the median roughly, but yeah, I mean, you can think about, if you think about the error bar, we should probably consider there. I remember there are definitely certain cases where it's very not overlapping, right? So if you look at the door, like the lower bar of the yellow is almost higher than the higher bar of the first purple.
Oh, I see. Yeah. Okay, I see.
Right, and then that's same for like hammer human as well. So there are cases where like at least our implementation cannot get the thing we want, and we believe that's mostly due to optimization issue, because we see that like when I set alpha to be lower, which is I want alpha to be slightly higher, it gets better, and we also know that like pi-ref is always a solution. So yeah, we don't have any guarantee on like how these things converge, whether to the exact thing we want in the two-player game or not in our deep learning implementation.
Okay, that makes sense. Thank you. I wonder if, so in seeing this, I wonder if there's any qualities of the tests that indicate whether or not, indicate anything about how alpha should be tuned. Because effectively it's another hyperparameter in a way.
Yes, so alpha is definitely a hyperparameter, and then here the only argument is that we are making is that like alpha, you have to tune that. We don't know how to tune that, but we at least have a direction to tune that from this RPI property, right? So we know that like if there's no optimization error, then I can start with alpha equal to, let's say, infinite, which will be 1 over alpha equal to 0 in here, and it will be no worse than what we started with, and then I can gradually increase it, increase 1 over alpha. And I should see essentially like a performance increase, and then it drops, right? So if I be very careful about this process, it becomes like more like tolerable, in the sense that I start with something I have, I try something, let's say I train this policy for different alphas, and I test it one by one by their ordering. And at some point, once I see performance drop, I stop. Then I can pick the best one in the hindsight. And so if you are allowing to kind of like do hyperparameter search for policies that are at least no worse than what you have, then that's a way to tune how alpha. But I think in general, like if you want to do this purely offline without any online interaction, I don't think there is a very systematic solution yet. That is kind of like, at least let's say a working practice, that to my knowledge.
Okay, that was I think going to be my follow-up question. Although, can alpha be changed during a suite of tests? I mean, I know that you are tuning alpha as you do multiple tests over a period of time. You go back and you look at which one, fit your expectations the most. But if alpha is adjusted as, say, the learner gains confidence in its approach, can you change that while the algorithm is running, or is it sort of fixed?
Well, the algorithm learning, do you mean like during the optimization process? Because here, at least in the offline setting, you have a fixed data set, right? So do you mean that like when I'm optimizing the policy, I change alpha during optimization?
Yeah. So in these cases, these were like entire runs with 1 over alpha 0.01, 0.05, etc.
Yeah.
In some cases, because you're looking at where alpha drops off in terms of performance, that seems like something that could, if you selected your I don't even know necessarily what you would have to do for this, but if you changed alpha as you were running these multiple policies, whether or not that would sort of narrow the amount of training you actually have to do in order to converge on this.
I see.
Alpha drop off.
I see. I think that's a very good idea. We haven't tried it. I think my intuition would be like a knitting schedule might work. And also in practice that like for this, let's say implementation to work, like the initialization matters. So in these experiments, we initialize the learner policy as a behavior clone version of PyRef on the data that we have. And so I think maybe, for example, starting from like alpha, let's say if I have a schedule of alpha by either exponential or like kind of like exponential schedule, and then I gradually say 1 over alpha from, let's say 0 to be 0 0.01, 0 0.1, etc. And I wait until it is I optimize it in this order, and then for trying to converge, that might actually lead to a good optimization curriculum, but I don't know whether that will actually work. That's just my intuition because I haven't really tried and tested it systematically yet.
That's fair. I bring it up mostly because, as you pointed out, you don't have it. There's not really any guarantees on the performance bounds of doing something, especially if you're training transformers or anything that has like a huge amount of.
But I think this is a very cool idea in the sense that I feel like this kind of like trend about how things should at least symptomatically work with alpha. If we don't consider optimization, we know that for sure, but that's something we can analyze. On the other hand, like I think the idea of me using this kind of like trend to design a curriculum for optimization seems to be very compatible with each other, because during the way you also get these like intermediate checkpoints, right, for free, and then so somehow they seem to be work very nicely with each other, and so I think that's a very good idea.
Thanks also in this presentation for bringing a practical or a concrete example of this in practice. We get a lot of theory and not a lot of, oh, look at that, it worked.
Yeah.
So thank you for that.
Yeah. Thanks for the questions.
Right. So I had a question regarding related work. So there's this paper that you're also showing in your comparison, is this attack paper. That's your paper too, right?
Yeah.
Right. So to my understanding, that is very similar to the idea that is under Armor. So can you explain like the difference between attack and Armor?
So attack is also centering about the idea of minimizing performance difference. So it's like also based on the relative pessimism kind of route. So it belongs to, I mean, it's kind of like it's the left wing of this classification. The difference is that like attack is designed to minimize the difference to the behavior policy, and that's because that's something you can estimate it without a model by just looking at the data, right? So the reason you can see that is if you look at this second line here, if I change the PyRef to be the behavior policy, if that's what I want to minimize, now you see this would be just like the difference between Q values under the data distribution, right? So now I can estimate this objective by just learning the critic without touching any of the models, etc. And so a text design based on that. So it only learns the critic and learns the policy without learning any of the models. And so so you can, so it has RPI to the behavior, but not to other policies. And so, but the issue we found, or the limitation we found later on, is that like oftentimes the behavior policy is not a policy that you care about of improving on, because usually you have like data collected by multiple policies. And that's especially true when you are thinking about like you are building a system for multitask application. You have policy for different tasks, and you have all the dynamics data that are kind of shared, right? But then like you only care about your current task, and that's your PyRef. And that's what kind of motivate this work.
Right. Yeah. I see. And yeah, I also remember something in the paper about PyRef not necessarily being a fixed policy, but maybe like something else. For example, like the best policy within the model. So like PyRef could depend on the model itself.
Yeah. So in the paper, we actually have extensive discussion on like what PyRef should be, right? So like so for example, this kind of related to this idea or the remark I made earlier on, which is this one. Like if you think about this as an operator, I give you a kind of reference, and then you output the policy. So this is something you can iterate over, right? And there are actually many policies that you cannot really iterate, right? So one, so like Pi has you get from like Armor here is one example. Another example would be if I set the PyRef somehow to be the optimal policy of one NDP instance in my model class M alpha. In that case, that policy will also be the solution as well. So there are some kind of PyRef that are really like the what we say kind of like the one that witnessed the worst case. And so those are the ones there's no way to kind of like uniformly improving that over your uncertain set of models. And so there are also, let's say, PyRef that are kind of like, let's say, you get from any kinds of regret minimization kind of framework, where I minimize say of pi minus plus another regularization. So if you get something like that, it will now also like how to improve in here. So those are essentially, they are thinking about, I mean, and we are thinking about this is more like multi-objective optimization problems. There are essentially some kind of like Pareto frontier, which are those are a fixed PyRef, where there's no way to systematically improving all the dimensions, and where each dimension, in terms of like interpreting this as a multi-objective optimization, is the performance in one instance MDP in the model class, right? So you have this like multi-dimensional objective. You want to, let's say, find a policy that are better than what you have in all possible NDPs that are consistent with the data, but you don't know which one is the truth. So you want to find the one that's uniformly better, but there are some policies that you cannot do that, because they're already like at least like the frontier in these optimization.
Right. Yeah. So regarding these fixed points, so what can you say about these fixed points? I mean, are they bad, or do you have some examples when the fixed point is like some really unreasonable policy? So why is it a bad thing to have fixed points?
So I think you can definitely, the fixed point can be definitely bad, and there are definitely bad ones, right? So for example, as I just mentioned, like if I pick any model from this M alpha class, and its optimal policy will be a fixed point, right? So it means that like for example, like if I run let's say an optimistic version of this, right? I want to have a set of models. I pick the one that has highest return, and then find optimal policy in there. And I usually will run that and to exploration. I can prove that it will converge, right? And and that one is also a fixed point. That's something that you cannot really like rebuke in the offline fashion. That can, because in the worst case, that can potentially be the best policy. And then this is really telling you that like in the offline case, when you have like uncertainty that you cannot, let's say, remove because you cannot collect new data, like there are many policies that you cannot say strictly one is better than the other one, because there's always some case that policy might be better than what you have. And that's why that's kind of coming together with why I said at the very end of the talk, which is that like how to choose among them is really subjective. Like if you are saying that, yeah, I want to follow in offline RL, I want to follow this kind of optimistic solution, I cannot really say that's the wrong thing, because I cannot really prove that you are wrong, because I cannot find a policy, at least in this worst case scenario, that's better than yours. And that's kind of very kind of like interesting philosophical question, I think.
Right. Yeah. Okay, so if there are no more questions, then we can stop the recording, and then I get to ask the usual question about off-policy reinforcement learning.
Okay.